This conference will now be recorded.
What do you mean by FPGA? So you have this CPU, right? Please be interactive. Actually, so this is like not some theoretical course, right? So unless you interact, have doubts, so it will not be useful. So what do you mean by FPGA? What is the difference from CPU, GPU, or ASIC?
FPGA is a kind of a SoC which can be reprogrammed or it can be reconfigured as per the requirement of a specific or any kind of application where it is used, not like other specific ASIC based SoCs which is mainly used for the particular application purpose.
Right. So this is actually a reconfigurable circuit, right? I mean, if I consider an ASIC, like for any of the application, right? Like if I have, let me consider a small example, like a counter, right? So I cannot reconfigure it. Like if I have a 10-bit counter, for instance, I cannot reconfigure that for like 16-bit counter, or I cannot reconfigure it for adder, right? So whatever the ASIC is designed, that is the fixed circuitry. It cannot be reconfigured, right? But whereas in FPGA, it can like wear a different masks, right? I mean, like now, if I say this FPGA can act like a RISC-V processor, like later by modifying its configurations, right? So I'm able to make it like a 5G processor, right? And later I can make it like a simple, I can make it like a small AND gate, right? That all depends on the resource, how much resource available, right? Uh, yeah, that is one thing compared to FPGA versus ASIC. I mean, ASIC is a fixed configuration. I can modify the configuration and I can make act like a certain circuit. But same thing is possible with the processors also, right? I have a microcontroller. So microcontroller, I can make it like a RISC-V processor. I mean, like the functionalities I can make ideally, right? I can using GPU, I can make a CNN algorithm. I can build a small counter, right? But what is the difference between general purpose processors and FPGA? Like you have a processor, microcontrollers, right? What is the difference between these controllers or microprocessors and FPGA?
Sequential and parallel execution.
That is, yeah, true. Actually, the flow of execution, sequential and parallel execution, that is true. In a
Those are
microprocessor,
those are finite
every
state
instructions
which is programmable.
will be executed. Pardon, Prashant?
Those are
Can you
finite
repeat?
state things, and this is programmable. Like we can remodel this as many times as we need, basically.
Yeah. So see, actually in the processor, what is happening? So when I'm saying like I'm having a program, for instance, like let me say that I want to add like y equals to a plus b and uh, z equals to y plus 6, and let me say that like I have L, that is z into y. So what is the flow? I mean, if I consider now a processor and FPGA, how it will be executed actually? If I have a processor, for instance, in the processor, how it will be executed, and in the FPGA, how it will be executed.
Processor, it will be sequential, and FPGA may be concurrent, maybe sequential, both the way you design the circuit.
Correct. So basically, when I say I am executing this on the processor, right? So this will be kind of sequential, like, I mean, in the program memory, each instructions, right? So each instruction will be actually like, I mean, if I want to execute this, so first I need to load A, right? I mean, like if I'm building a circuit, I mean, if I'm converting this into assembly program, so I have to load A to certain register, load B to certain register, right? Load A to register to R2, right? So I mean, then like I have to add R1 plus R2. I have to store in R3, right? So then I have to load this Y value. Then I have to add a fixed value to 6, and then I have to load value of Z, and I have to load value of, and I have to pass it to the multiplier circuit, which is again ALU, right? I mean, see, addition, multiplication, everything is using a single ALU, right? I mean, that actually step by step, like sequentially. I mean, if I consider a timing diagram of it, every clock cycle, basically after the another, this executes, right? Because why we can have like all the things parallel? No, because I have a single core. I mean, I'm talking about a single core processor. So I have a single ALU for addition, subtraction, multiplication, everything. It has to like through this first, it has to go to this ALU, and I have to get the result, store back to original register. I mean, wherever the intended register is there. So I have to store there, right? So that is a sequential execution. But in case of FPGA, what I'm doing, I mean, like if I want to have a parallel execution, I'm not, these are like not treated as a instructions, right? In FPGA, these are like not treated as an instruction. If I say I'm adding these numbers, right? If I'm adding these numbers, then what is going to happen is basically for this, a fixed register will be created, right? So if I say this is R1, so a fixed register for A will be created. If I say it is like 8-bit, fixed register will be created using flip-flop. And for this B, another register will be created, right, of 8-bit. So this for adder, right, I'll be having a separate adder circuit. And same way, like here it is Y. So this Y will go to another adder circuit. And here I'm adding 6. And parallelly, whatever the Z I get, so I will have a multiplier circuit, and I'm multiplying with Y, right? So this is the difference. I mean, like previously, everything was going to the ALU, and in the ALU, executing instruction after the instruction, right? Now here, everything like executed parallelly. There is no, I mean, if I actually model it as a combinational circuit, whole thing will be executed in a single cycle, right? I mean, like here I haven't brought the clock concept at all. It's a purely combinational circuit, right? Like there will be a combinational delay. Apart from that, like it will be executed in a short duration. There won't be any delay as such, right? Only the combinational delay. And for instance, if I want to build something like that sequentially, like one after the another, that is also possible. I mean, any tip, as somebody was saying. So if you want to build like sequentially, right? So that is something like you have to write a finite state machines for that. So in FPGA, everything is possible. I mean, like you can have a behavior like a processor, or you can have a parallelized behavior. That is why nowadays, if you see any of the artificial intelligence or data centers, nowadays they are talking about like FPGA based solution, right? So I mean, many have a misconception that like FPGA only used for prototype before the ASIC implementation, right? So no, it is not the case. Like all your satellite applications, defense application, data centers, right? Even healthcare application, like you might have seen MRI scanners, X-ray scanners. That all these things are using FPGA as the processing unit, right? It is like because, uh, for instance, now let me say that like I have a application, like for example, a space application. Uh, like hardly I may launch like 5 to 6 satellite, right? I mean, with the specific configuration. So if I am planning to build a ASIC for it, it is unnecessary. Or I mean, it's a kind of like waste of resource, right? I mean, like so usually, as you know, like even if you build 1,000 chips or 2,000 chips, so basically the cost associated with that is fixed because like you have to do a lot of configuration to etch that circuit, right? So in that scenario, when we have a limited application scenarios like base stations, 5G base stations, where you have like hundreds or 200s of units of products, so still you use FPGA based solutions itself. Nowadays, if you see like in Bangalore itself, there are like lot of openings in terms of FPGA designers. That is not only for prototyping, that is for the actual applications itself, right? So this FPGA will not be used only for the prototyping, it will be used for the actual applications where we need acceleration, like artificial intelligence acceleration in the data centers, right? Nowadays, like even Bing search engine, they are using FPGA for their search engine optimizations. So we have to keep in mind like how this will be used and what kind of configurations, how this is executed, right? So that kind of understanding we have to build first. And the very important understanding you should have before taking this course is the parallelization. Many times we'll have this software thinking that is like everything will be executed one after the another, right? So that is not the case here. So the way how you design it is based on that the code what you write, the Verilog or VSTL will be executed here, right? And one more thing you have to keep it in mind here is the timing thinking, right? So every line of the code you have to think like in what clock cycle it is going to be executed, right? Here clock cycle based thinking is very important, right? Every single clock matters here in the processor. Do you mind like I mean how many clock cycle? Yeah, when we talk about optimizations and all, we think about like how much time it is taking, but many a times we keep writing the program in software side, right? I mean in the processor or microcontroller we keep on writing the code, right? We are not much bothered about in which clock cycle it is executed and how it is going to be executed, right? So here it is very important to keep in mind that everything is clock related, right? So we have to understand that clock by clock execution of our program, right? So another important thing you have to understand in this course is I talked about like these circuits are going to be created inside the FPGA, right? How these circuits are going to be created, right? I mean, like, so even to generate a simple counter in our digital labs during our BTech or masters, so you have seen that like you have to connect that IC, place that IC, right? So there will be a lot of connections, routings. How this dynamically, these routings and placements, everything is taken care in that small chip, right? So for this, the fundamental aspect of designing in the FPGAs are basically MUX, right? MUX based design, right? So, do you know if I have a MUX here, say I have a MUX, one MUX. So, this 2 is to 1 MUX, can I convert this into AND gate? If I ask you to convert this 2 is to 1 MUX into AND gate, how do you do? If this is like A and this is B, this is Y. So in your digital electronic, you might have studied like conversion of 2 is to 1 mux into AND gate, OR gate. Do you remember that? How do you convert that? if I convert into, this is like, I mean, whenever you attend any of the digital interviews, right? So that is also like frequently asked questions, I can say, FAQ. So what is the way to convert this 2:1 mux into AND gate?
So it will be like the control line is one, then A will go, let's say. Then there will be one AND gate for passing one control line will go to two AND gates, like one AND gate, or maybe the other is 0 and
So
1.
actually, like now if I say, so this is Y, okay. So AND gate is actually uh, L, M, N, okay. So can you say like where I have to connect L, where I have to connect M, where I have to connect N? So you have to map this, right? So you have to actually map this to mux. So how do you do that?
L connected to Y, like select line,
This is Y,
and
I guess.
M
L connected
connected
to select line.
to,
Okay.
yeah, M to the B, and
Here I connect B to M. Okay.
A to the ground.
A to ground. Okay. So now what will happen? Like, let's see, like now I have M, L, and Y, right? So you have connected L to the select line, right? 0, 0, 1, 0, 1, 1, right? Now let's say L connected to 0, right? So in that scenario, your Y will be 0 because you have connected A with the 0 ground. L is 1. L is 1, so it is going to be M, same as B, right? I mean, it is same as M, so it is 0. Now L is 0, so since you have connected to ground, it is going to be 0. And since you have connected 1, so it is going to be 1, right? So this will work. But how did you arrive at this circuit actually? Is it just trial and error method? There is a proper way to arrive at this circuit. Anybody? So basically, we have to select, when I have two inputs, right? I have to select one of the inputs, right? This is select line now. M select line, right? So now you can see the relationship between L and Y now. When M is 0, basically it is going to be A, right? So A. So when M is 0, so you can see Y is always 0, right? Y is always 0. When M is 0, Y is always 0. That is why I have connected that into ground, right? And when M is 1, you can see L is same as Y, right? L is same as Y. That is why I have connected that into L. Did you understand this concept? So this is very fundamental aspect how this FPGA creates the circuit. So I'll try to connect that concept, but you should understand this first. So anybody has any doubt here? Any questions here?
No, sir.
Right? So same way, can you help me to convert into XOR gate? How do you convert into XOR gate? If I have 2:1 mux, I have A, B, Y, A, B, and S. So if I have XOR gate, which
Sir,
has
A becomes B complement.
this is Y. Okay. Yeah. So XOR gate A, B you have, and 0, 0, 0, 1 0. So you mean to say B bar, is it? What to connect for the select? How do you design this?
Sir, inputs are B complement and B.
Yes. So here B complement and B. What about select line? I have to connect with A, right? Because when it is 0, my select line is 0, my output same as input, right? But when select line is 1, it will become B bar. Is B bar. Anybody has any question? It's clear, right? Do you want me to take another example? See, before we talk about FPGA or any complex things, we should understand these fundamental aspects. Everybody clear? If no answer
Yes,
means
sir.
it's clear, right? Okay,
Yes, sir.
fine. So now, how this is utilized? This concept is utilized in the FPGA. So the fundamental building block of FPGA is something called lookup table. Okay. So lookup tables are nothing but a SRAM based memory. Okay. If I say it's a 2-input LUT, so I will have 2 lines as address for that. And I will have 1 output. Okay. So in this memory, right? So if I store 1 0 1 0, this is like 1 bit memory you can consider. So like if 2 address bits are there as an input, 1 output is there. So for every input, I mean whatever the address you give, so that corresponding location you are going to get as output, right? So now if I say my address is 0 0, you're going to get 1 as the output, right? If my address is 0 1, I'm going to get 0 as output, right? If it is 1 0, you're going to get 1 1 1, get as 0, right? So this is a memory, and you have a 2 inputs of address, and you have an output, and whatever you program, you're going to get the output, right? I mean, like based on the address lines. Now, can I say using this memory, I can realize any of the 2 input gates? Can I realize? So, I mean, whatever I program, so you're going to get the output, right? So it's a memory. So can I say that like, I mean, can I realize AND gate using this same concept? Can I design? Is it possible? Can I design an AND gate here, OR gate? Like, I mean to say that like I have to replace that data here. I mean, see, now it is 0 1 0 1, right? So I will replace this data with 0 0 0 1. Now, if I connect A and B here, so now it is acting like an AND gate, right? So if I replace with this way 0 1 1 So now this is a OR gate, right? I mean, are you getting what I'm trying to say? Yes or no? You want me to repeat?
Can you
Yes
please
or no?
repeat?
Oh, yes. I have a memory, okay, which is of 4 bits, right? So to access these 4 bits, how many lines I need? I mean, if I want to individually access these memory locations, how many address lines I need?
2.
Two address
2
lines.
address lines, correct? 2 address lines. So one output is there. Whatever the address I give, I will have one output. So now I will connect A here, B here. That is the input to the AND gate. Y to here. And I program these memory locations with 0, 0, 1. Right? When my input is 0, 0, I'm going to get 0 as the output. When the input is 0, 1, I'm going to get 0. 1, 0, 0. When input is 1, 1, because I have programmed 1 here, I'm going to get 1 as the output. So now, can I use this memory as an AND gate? Yes, right? By programming of this memory, I can create this as an AND gate. This memory I can utilize as an AND gate, right?
Yes.
Same way, same memory without changing any circuit. If I reprogram this memory with OR bits like 0, 1, 1. So I'm not changing any circuit, just reprogramming these memory locations. I'm making this memory as an OR gate, right?
Yes.
Yes or no?
Yes, sir.
Yes. So let me say I have a circuit like this. A, B, and Y. So what is the truth table of this? Can someone tell me? So I have A, B, and what is the truth table of Y?
Zero one zero zero.
0, right? So ideally, if you, I mean, in the hardware, if you want to implement this, you need like 2 gates. One is NOT gate and AND, right? But do I need to have another memory like this? No. With the same memory, can I implement the same thing? Program 0, 1, 0, right? If I program 0, 1, 0, 0, the same memory will act like this particular circuit, right? So basically, LUT doesn't care about what circuit you have. It cares about how many inputs you have and how many outputs you need. Same way, 3 inputs, right? 3 inputs. 3 inputs, how many, like if I have 3 address lines,
Eight
this is 3
locations.
inputs. How many locations I can have?
8.
8 locations.
I can have 8 locations, right? So now I have a circuit. Yeah, I have a circuit. This is A, C. You have to have NAND gate A, B, C, and Y. So if ideally, if you are implementing this on ASIC, you need to implement this every circuit, right? I mean, every gates you have to implement. You have to consume certain transistors for this, right? So even if you are implementing this on a hardware, you have to do lot of you have to put like lot of ICs and all. But as per LUT, this is based. So like in the FPGA, right? Basically dealing with LUT, where like basically your input matters. Like you have to feed A, B, C, and do you agree for whole circuit, even though it has lot of gates, it will have only 8 possible outputs? Do you agree with that? Even though you have this many gates, can I say for the possible inputs A, B, C, you will have only 8 possible outputs, right? Because like inputs are like only 8 possible inputs. Do you agree with that?
Yes, sir.
Right? So what I need to do is like your EDA tool, it tries to understand the possible outputs of this Y, whatever the Y you get, and it is going to program those areas. So same, whatever the circuit you change, right? I mean, not gate, or you put another like AND gate, or XOR gate you replace with a NAND gate. So this circuit, what you have inside the FPGA, it is not going to change. That's the content of the memory is going to be changed. That is why when we program to the FPGA, we do not say that like we are programming to the FPGA. We are configuring the FPGA for particular circuit. And at the end, whatever the file we program to the FPGA, what we call that file as? Is it
Bit
a bin
file, sir.
file? It's
Bit
a
file.
bit file. It is a bit file. Why? Because we are configuring each bits of these memories. That's why we call it as a bit file. Clear? So ideally, I mean, it won't be 3 inputs like in 7 series FPGAs and all. It will be 5 input LUTs, right? So any 5 input configurations, right? So you can have like, let me say you have 5 input. Internally, you consume like 30, 40 logic gates. It doesn't matter for the FPGA. Everything it will compress into a small LUT, right? So we'll see with the tool. I'll show you like various scenarios how it actually compress into small LUT. You can see it in the EDA tool also. Yeah.
Sir, I have a
Any
doubt.
questions so far? Hmm.
The whatever LUTs you discussed related to the FPGA, whether these LUTs are configurable to different sizes or it is defined
No,
with a limited number of memory locations, whatever you said, is fixed for the FPGA to FPGA, or it can be configured from minimum to maximum, like how it is defined
no.
and how.
So in a FPGA, so the size of LUT, like I mentioned, 5 input LUT, right? So 5 input LUT is fixed. Okay. When I say it's a 5 input LUT, like let me say you have a 10 input function, right? 10 input
Mhm.
function. So you have a question that like, how do you use this 5 input LUT? So it is actually cascading of these LUTs. We have to use the cascading of these
You
LUTs.
mean to say like
You
we
know,
need to
like,
use two LUTs for 10 different
correct,
inputs? And
correct.
like how do
So when I
you
say, yeah, go ahead.
yeah, yes, tell me, sir.
So actually, whenever like now I say that like what is the limiting factor in the FPGA, right? It is something like uh, when I consider an FPGA, when I want to select an FPGA for a design, I see how many such LUTs are available in that FPGA. So basic thing what I look in the FPGA is how many LUTs in a given FPGA. So the cost size of the FPGA based on this LUT sizes itself. So you will get like 5 input LUT, 6 and input L, no, 5K LUT, 6K LUT. Nowadays, your ARIA 10, like which is from Altera, even we say ultra scale devices, right? It will have billions of LUTs. So it's basically like how many LUTs available, right? That matters. So when I say now you are designing one 5G system, right? Even like single FPGA may not be sufficient because of the constraint of the LUT. So it is something like, it's like a Lego, you know that, like you have a limited blocks. So that is the whole, I mean, as the FPGA engineers, right? Our objective is to fit the design in that small given area. But in case of ASIC, it is not like that. You are deciding, I mean, you can put like as many circuits you want. Based on that, you are deciding the size. You have the flexibility of that. I mean, customer may have given the area requirements, but still you have, I mean, if you want to fit more in that ASIC, still you can slightly increase that area, right? I mean, area can be increased in that. You have flexibility. But here everything is given. You have like fixed number of LUT you have. It's given by the FPGA vendors. So you cannot have like more than that resource. So you have to play within that LUT.
And each LUT will have a fixed this address locations, like 5 input LUT, 10 input LUT. That will be
Yeah,
fixed for all the
there
LUTs.
is nothing as such like 10 input LUT. So I mean, I think 5 and 7, I'm not sure. I think ultra scale I have to check again. So there is like different LUTs. Like in olden days, you used to get 3 input LUTs. Now 5 input LUTs. With that itself, we have to play.
Okay.
So it is something like, see,
So
lesser the inputs, lesser the inputs, you can play more. Because for instance, if you use this 5 input, using 5 input LUT, if you utilize all the 5 inputs, then it's a optimally used. But let me say that you have only 2 inputs, then like only 4 location will be used, rest of the locations will be
location.
wasted, right? So lesser
Correct,
the
correct.
input size is available, so you can optimally use this LUT for your applications.
Okay, sir. Okay.
Any questions here? Okay, so now some may have question like, this is one output, so I want to cast the circuit, right? How it happens in FPGA. So this is routing. So such I said like millions of LUTs are there. Permutations and combinations are multiple. So for the routing, I mean, apart from that, like we will also have configurable registers as well. So this is combinational circuit, what I said, right? So if I want to make, so if I connect one flip flop here at the output, connect to, like we have like configurable flip flops also. Okay? LUT, then flip flop, it will, then how it will be connected to flip flop, right? So we will have configurable switches. So it is something like this. You have a wire, right? So MOS and actually up a bit. Whenever you enable this MOS will be on, right? So this way, programmable here in the FPGA will be programming the routing as well. Okay, that is the whole concept behind the routing as well. Yeah, and flip flop, we have this input, and routing also it can be programmable. And here we need not. And one more thing. So once you write the RTL, so in physical design, I mean like RTL to GDS flow in ASIC based designs, what you do, you may have to like have lot of manual interventions, right? I mean, you have to place route manually sometimes. But here, most of the cases, it is tool oriented. It's a vendor specific. You can give the optimization strategies. You can say that like where in which area you want to place this circuit. Right? Those are there, but using constraint files, you can give it that. But apart from that, most of the things will be taken care by tool. So initially in the RTL and in terms of timing constraints, you can tell the tool, but you need not bother about the physical design of it, like how exactly it is going to be placed and routed and how the bit stream is generated. So it is all EDA driven. Yes. So this is like whole fundamental aspect of the FPGA. But having said this, so let me just go through what we are studying, what are the different aspects we'll be studying. Okay. So it is not limited to whatever I am presenting. So there will be like, as and when that I'll be covering. So coming to the history of FPGA, like initially first programmable FPGA was introduced in 1983 by Altera. I mean, it started with the Altera, then it commercialized by Xilinx. So these are the vendors who actually started the FPGA. So now I think Altera, this is like little older data. So Altera was 31% like in 2003 and Xilinx was 36%. Now it is almost equal. I mean, Intel is also coming up, right? So Intel, they have separated again, they merged and they separated because of they realized that like how FPGAs are important for the artificial intelligence, data science. So FPGA market is growing like anything. So in 2015 they acquired, they merged, then they again like recently in 2024 they came out, right? So search engine like Bing, Microsoft Azure acceleration, everything happens on the FPGA. So coming to the application, so as I mentioned, ASIC prototyping is one of the application. So many a times when I discuss with like many people, right? So when I ask and talk about FPGA, they only think about it is for prototyping. Apart from that, I think prototyping 10%, 90% of the share with data centers, communication, aerospace domain. Now we talk about autonomous vehicles. So all these things are using FPGA instead of processors, okay, because of its computation power. So in the data center, image processing, network acceleration, financial technology, database, 5G wireless, communication, right? Wired communication. So you can see in 2020 it was 10 billion. Now it is like keep increasing exponentially, right? The revenue of the FPGA. So coming to architecture, right? Inside the FPGA, I was just discussing about lookup table. So you can see this is a 4-input lookup table, and you can also see how it actually multiple lookup tables are combined, right, using multiplexers. And also it goes to like basically using mux, right? It goes to flops. You can also see there will be direct path as well. If you want to have a purely combinational logic, this mux will be, this flip-flops will be bypassed, right? This is how we basically design a circuit inside the FPGA. Okay. So basic advantage of FPGA is flexibility, which designs any digital design using same chip. That is the advantage of it. Okay. So in FPGA, right, we also have something like SoC. Nowadays, this is one of the popular trend with the FPGA. We also get something like SoC, right? FPGA SoC we say, right? Here, what is happening is I have a FPGA core. I was talking about acceleration, right? Like let me say I have an operating system running, okay, like Pita Linux or Linux operating system running, and I want to accelerate certain part of the system. Like let me say I have a real-time image data is coming. I want to compress in the shorter duration. So for such application, I need a processor also. If I want to run an operating system, that is not a good way to run that on the FPGA, right? I cannot create everything on the FPGA, right? I mean, see, when I say FPGA is faster, it doesn't mean that like all the things what I'm running on the processor I can push into FPGA. There are its own drawbacks, right? Let me say I have an operating system. It is like there is no requirement that like every functionality of the operating system has to be run parallel, right? So it is like application oriented. So whenever I am designing a certain application, I have to think what part of this application I have to program in the processor, what part of the system I have to parallelly execute. Because you say that like I have to have like A equals to A plus B, A equals to B plus C, and like such 10 instructions. If it is okay that to perform in the 10 clock cycle. I mean, if it is like sequentially is also fine. I mean, I don't have any timing requirement of it. Then it's unnecessary wastage of resource to construct a circuit for that. It consumes like almost 10 adder, right? Maybe like 3, 4 flip-flops. So what is the disadvantage if I mean, see, it will be faster, right? It is advantage. Can someone figure out what is the disadvantage if I do that? Like, I mean, my timing is like, I'm okay with like 10 clock cycle, but I try to design a parallel circuit using FPGA. Still, timing wise, I have an advantage. Like in 1 clock cycle, it will be processed. When it is faster, what is the disadvantage? Can someone figure out what is the disadvantage? What is the disadvantage? When I have more circuit, what is the disadvantage? It consumes more power, right? Hello. Power consumption. Yes. Because previously only one adder was there, right? One adder was there. And same adder was. So this, when I say one adder circuit is created, it is actually consuming power for only this adder. And area wise also small, right? Now I need an area of 10 circuit, 10 adder. So even though you have an advantage on the speed, so basic objective of or like basic trade-off of VLSI is area, speed, and energy, right? So we tried to improve the speed, but it was not necessary. Because of that, area also increased, energy also increased. But our objective was to, I mean, whole objective is to decrease the area, decrease the energy, and increase the speed. That is the real-time objective, right? But we try to play with this strategy, but other two parameters got affected, right? So we have to carefully select which to program in processor, which we have to put into FPGA. Whenever there is a need to accelerate the things, then only we put into FPGA. So nowadays we get something called like this processor hard IPs, right? Within the FPGA itself, you might have heard about Zinc processor, Cyclone 5, right? So these are actually FPGA SoCs where you will also have processor. Okay, so here you can run the embedded software also parallelly, whichever the things need to be accelerated, that you can put it on FPGA. That we call it as FPGA SoC. Clear? So you can see nowadays, like even Xilinx has come up with RF chain with that, right? The things are getting more and more complex. So this we call it as RF SoC, where even like 5G, ADC, DAC, RF chain also integrated within FPGA as a hardcore. I mean, you need not bother about implementing that or externally connecting that. So coming to the ASIC versus FPGA, FPGA can be used for lower volume application, as I was mentioning, like your satellite application, 5G communication. Whenever like you have a mass production, like mobile chips, right, or smartwatches, where like millions of units you are going to produce. So in that scenario, ASIC is usable. Okay, so FPGA can be programmed even after given to the user, right? So coming to the development tool, we in this course we use Vivado. I recommend everyone to install this tool. And Quartus Prime also you can install. That is an Altera based FPGA. And basically simulation tool we use Model Sim. Okay, Intel Starter Edition is there, so you can use for simulation purpose. Okay, so what are the things we are going to learn in this course? So we will start with the FPGA design. So today I just gave you an example of basic LUT component, how that is going to design, but we dive deep into that. Okay, so we will see like how these LUTs are mapped in the Xilinx FPGA. What are the different types of LUTs are available? How memories are used? Like we talk about block RAM memory, DDR, right? What is preferred? When to use those memories, right? And we see the FPGA architecture of it, and we give. I'll give you some little bit information about HDL aspect of it. I mean, so coming to FPGA, you have to write like FPGA specific HDL. I mean, there are some optimized way of writing HDL for FPGA. So this is very important, like for the ASIC engineers also, when they port, I mean, when they want to test their ASIC designs on the FPGA, so they may have to put certain constraints. They have to write in certain ways, right? So that is very important. And as you know, I mean, as a FPGA engineers, we have a flexibility to become an RTL engineer. We can design our own IPs, which can be portable for the ASIC, right? So how we can actually, or the RTL we have written, how we can put into IP core, or like existing in the FPGA toolset itself, there are existing IP cores, how we can reuse that, right? And we also talk about synthesis flow, FPGA simulation, like implementation. So, I mean, many think that like FPGA synthesis implementation and bitstream generation is just a tool oriented flow. But there are many things associated with that. You have to do the time, you have to do the power analysis. You have to analyze each net. There is something called optimization, P block optimizations, right? How we can do that. And timing simulation, like with the timing, how we can simulate the design, right? So many times what happens is like we keep debugging the design. It is not working. Majorly because like whatever you have simulated, just behavioral simulation. You haven't considered the time delays after routing and placements. So as I said, every clock cycle matters, every millisecond or nanosecond delay matters. So because of that, you might have ended up in setup and hold violation. So in the board, it will not work. So before putting into the board, you can have timing simulations. So that we will be studying. Okay. So you also have system level testing and debugging. That is very important. So as a design engineers, right? So maybe like we may spend 20% of the time in designing and 80% in debugging skills. So to accelerate the time of development, right? So I mean, like we have to know the optimal way of debugging, right? So that is where it is very important. There are like various debugging techniques in the FPGA. So we say ILA based debugging techniques, VIO based signal. In Altera, we have signal tab based debugging techniques. So what are the considerations we can do in that, right? So I will be covering that. And as I mentioned, so we also have nowadays like SOC based environments, right? We call it as FPGA SOC. How we can deal with those FPGA SOCs, like how we can program the software aspect of it. We call it as a high level synthesis, right? So how we can deal with the high level synthesis. So those things we'll be discussing. Coming to lab, so we will have like we want to IP integrator flow, how to create your own custom IPs, SDK based experiments, software debugging, also ChipScope Pro, right? Software application discuss. And if you want to run a Linux on the FPGA, that is a system on chip, how you can do. So those things we will be discussing. Okay. And as I said, so we will take one real-time project. I expect everybody to take one real example or project and try yourself. So that will help to see the real-time issues when you try to experiment or like when you try to implement any of the project. Okay. So this is the overall flow, what I'm planning as a part of FPGA course. So I mean, as you have already or like you might go through the basic sessions, right? The Vivado or this Verilog or scripting. Apart from that, this is the FPGA part of it. And I think you'll also have the verification separate verification course as well, right? If you are part of design and verification, that is separate actually. Verification is separate. But as a part of FPGA, you will be learning these many things. So any questions, queries, or concerns with this?
Sir, is there any verification part required for FPGA design?
Yes, as a FPGA designers, I mean, there are like two, even in the FPGA, like as you know in the ASIC, there are two roles: FPGA design and FPGA verification, right? So whatever the design you have done, like general UVM based flow, what you follow in the ASIC, right? That also has to be followed here. But basic level of verification, functional verification, we have to do as a designer, right? I mean, whatever the RTL code we have written, first level we have to simulate that, correct? So once we are satisfied, so all the corner case, the verification engineers will be testing that. But as a functional, as a designer, we should know how to simulate functionally. So before giving to the verification engineer, you have to make sure that whatever you have written, that is working, right?
Like once the design is done on the FPGA part, so
Hmm.
when it is in on the hardware, like is there any specific role requirement once it is onto the hardware for verification purpose?
Yes, that is if you see here, I mentioned about debugging using chip scope, right? That is actually like on the hardware. Like when you actually like put the FPGA design on the hardware. So if you want to debug whether it is working or not, then we have to go for a chip scope based mechanism to debug it, right? So those things, like if you want to debug the high speed interface, so we have something called IBERT based debugging. So we have to see those things. This is onboard debug.
That debugging part will be covered in this
Yes, 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 yes.
uh, like related to the some of the application specific, like some of the debugging scenarios where we can throw out in the design,
Yes, yes, yes,
like as you said, with the help of chip scope, like how do you how we can simulate the failure part of the design with the help of chip scope, and identify where
yes,
exactly the problem or the fault is being diagnosed, so that it can be taken care of further. It may be either related to the hardware part, or it may be related to the design code what we have written.
yes. Those things are there actually. I will be covering. So there is like not only that is chip scope is basically monitoring, right? Same way we can feed like error cases. Like if you want to feed some noise or error, we have something called virtual inputs, right?
Mhm.
So that also actually how to feed that VIO based concepts I cover this.
Yes, sir. Okay, sir.
Any other queries? Okay then. I mean, today we will not have any assignment as such, but from next session onwards, we will have assignments, courses, everything. So you have to submit it, and I'll be evaluating and giving you the feedbacks. Okay.
Sir, I
So
have
thank
one
you.
more
So from
question.
next week,
But
hmm,
sir, excuse me, sir.
yeah, yeah, tell me.
Can you just tell me like what all projects will be covered?
Yeah. But as I mentioned, like usually, like we cover basic risk CNN architecture. Okay, and also like as a part of lab, right, we cover various interfaces like Ethernet, SPI, UART, right, and some part of DDS, signal generations and all, right? So apart from that, like if you have any specific project in mind, you can take up
Mhm.
that, and then we will discuss that individually. Maybe like I can help you out or guide you how to build those projects.
Okay, okay,
So people will take their domain specific projects.
correct.
So you can plan that as well. That will be more efficient for you.
So that will be good.
Because
Like
like
once we
whatever
are,
we discuss,
that will be good once we are thorough with at least
what I s-
the basics, and
no, I mean you are familiar with the Verilog, right? You are familiar with the Verilog and VSDL, right?
Yes, sir. But when it comes to the FPGA part,
Yes.
not that
What I suggest,
confident.
what I suggest, what I suggest is like you start coding your project.
Yes, sir.
And as we discuss these concepts, so I recommend you to put it on the hardware or like in the yeah, tool and start testing. So now, I mean, it shouldn't be like after some classes you start that. So from the first session itself, like that is like from next Saturday itself, you have to start
Hmm.
putting onto the tool and start testing it.
Okay. And one more thing, sir. Like sometimes if you miss out the classes because of some other reasons, whether we will be getting the recorded sessions so that we can just go through the sessions and we can
Yes,
learn the things, whatever is taught in the class and implement and get note down the assignments.
yes, yes, that is available. That will be there. That will be there.
And how about the labs? Because whether we need to purchase a kind of a, hardware modules for our
No,
testing purpose.
no,
Because
actually,
I
the one of the hardware is connected to the lab server, so you can remotely access. You can check with the admin, so you'll be able to
how do
access that.
you how we can visualize that one, sir? Like once we dump our code into the remote hardware, like what exactly
So
the
as I
functions
was
it has?
mentioning about a signal tap, right? So you can
Uh,
watch those signals, what are the intended signals using chip scope, signal tap. So you can see what is happening inside the FPGA.
that will be taught, no, sir. Like for the first time, if you want to
Yes, 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 yes,
like how
yes,
to initialize, how to access the VPN,
yes.
and the lab.
No, accessing the VPN, accessing the related to accessing the VPN, connecting to the tool. So please coordinate with the admin team. So they will actually help you out with the recorded sessions. So they will give you that. So you can like based on that, like it's a step-by-step guided videos are available. So you can refer that and connect to VPN. So access server access everything you have to get it from the admin team.
Okay, sir. Okay. And this Vivado tool, whatever we are installing, I feel like they are like a paid licensed version
No,
of
no.
Vivado.
So for 7 series FPGA, there is no license required. So many has that misconception that like you have to get the license. So for the basic FPGAs, right, like Zinc SoC and all, there is no license required. You just install, synthesize, it will work out. Only for the ultra scale devices now license is required.
But this Linux on SoCs and all, like they are on the
That also good.
high end
No,
version
no,
of
no.
the.
It is not FPGA, Linux on SoC also. It's 7 series FPGA. For that, no license required.
Okay, okay. And the whatever the concepts that will be taught in the class, so that will be like implemented even for the Altera based FPGA also, no? So where like
Similar,
some
yes, yes. Concepts are
cyclone
similar actually. Yes,
cyclone
yes,
FPGA based.
yes.
The concept wise on both the FPGA architectures, like the concepts will remain the same. Only the thing is like architecture may be the different.
In architecture and some of the notations may be different. So here we call it as LUT. There they may call it lab, logic array blocks, and also those kind of things may differ, but it's the same concept with the different terminologies.
So what will be the scopes, or like as a FPGA design engineer, especially whether it is mainly into the VLSI domain or it may be to the even into the application part of.
Yeah, into the application domain also, as I mentioned, like lot of scope in terms of application domain as well. So in the VLSI domain also, see now if you get into the FPGA scope, I mean FPGA design, right? You are not limited to just FPGA design itself. Later you feel that like you want to switch into the RTL front end job roles, right? So you will be considered as RTL designer itself because like whatever the RTL you design here and in for the ASIC, it doesn't change much. So like most of the FPGA engineers I have seen that like they have worked like so it is like sometimes they have these FPGA engineers they'll be working as RTL engineer somewhere else and again they'll switch back to FPGA engineers we can
Mhm.
actually switch between RTL and FPGA engineer. But purely on the RTL designer, right? They have a constraint that like it is difficult for them to switch into FPGA because they'll not be knowing about FPGA, right? But
Hmm.
as a FPGA engineers, we are knowing about the RTL concepts as well as FPGA. So we have add-on edge actually.
Okay, sir. Yes, thank you, sir. Okay.
Okay. Anything else?
So the classes will be conducted every weekend on same timing, or it will be like as per the
Same time. Mostly it
schedule,
will be same. It will be
10
mostly
to
it will be same. Yeah, 10 to 1 around. But
over,
if there's any
overall
changes, I'll let
duration, sir?
around 40 hours.
40 hours. Like
Yeah,
it may
total
stretch
40
to
hours.
like 2 months, sir.
Yes, almost. Yeah. Yes, almost 2 months. Yes.
Okay, sir. Okay.
Okay, sir. Thank you, sir.
Thank you.